and the speaker is Lucas, who is a product manager at Sunamp, which is a leading manufacturer of heat batteries and latent energy storage systems. Lucas has been involved with the European heat markets, and also he's got a particular focus of his work has been on heat pump market development. Before joining Sunamp, he was working with Delta EE. Okay, Lucas, over to you.
Yeah, thank you very much, Maru, and welcome everybody. It's a pleasure to be presenting to you this evening, in particular because today is, as you probably all know, a historic day. Not only because of changes in the political landscape, but also because today is the day when we will see this map here, which is the countries around the world which have signed and ratified the Paris Agreement, is going to be turning entirely green again. So this is a very important day for us globally in the fight against climate change. And it's therefore a particular great day to be presenting about heat batteries, and to tell you a little bit more about how we see thermal storage in general, not only heat batteries, but also other forms of thermal storage. But obviously, of course, in particular, heat batteries fit into the decarbonisation challenge that we are facing globally. Just a few words about Sunamp and our company. We were founded in 2006 by Andrew Bissell, a successful entrepreneur who previously had a business in medical imaging. And after exiting this business, was essentially considering what venture or what challenge to tackle next. And he was back then sitting in Portobello, which is the nice seafront in Edinburgh, in a house they had there right at the promenade, and saw that in larger storms, the sea was actually already reaching the promenade quite regularly. And reading about things like rising sea levels, etc., thought, well, this is not going to go well for my house in the future if we're talking about 2, 3, 4 meters of sea level rise. And that was really what was his kind of moment of epiphany, where he for himself decided that the next big challenge that he wanted to tackle was climate change. And he first looked essentially at what he could do himself to decarbonize his own life, and he looked at his house in particular and looked at how could he essentially take out all the carbon emissions from his building. One of the things that he consistently came across, no matter which option that he looked at, was the fact that you needed a lot of thermal storage, either for providing the hot water or for buffering heat that is generated anti-cyclically, for example, from solar thermal or other options. Over a quite long period, this led to the development of our core product, which is the Sunamp unique range of heat batteries. And they are essentially heat batteries in the size of 3 to 12 kilowatt hours, but we also have larger systems for commercial applications up to 80 kilowatt hours at the moment, and are developing systems in the megawatt hour range, which will require standard container systems, essentially. We've always put a very strong emphasis on quality and efficiency, and some of the things that we have achieved is, first of all, the highest rating for thermal storage that you can get, but also the quality of our PCM. But I will go a little bit into this later. In terms of the agenda of my presentation, what I want to talk about is, first of all, just very generally, What is a PCM heat battery, or thermal battery? I should actually be saying. What are phase change materials? I'm sure that most of you will be familiar with the concept, but I still want to make sure that we're all on the same page, and I will just very briefly speak about that, but also a little bit about their history and about the fact why they haven't been used very widely in thermal storage up until now. I will briefly speak about how they can be used more from an abstract theoretical perspective, because in the later part of the presentation, where we'll be speaking about how they can be a part of the energy transition, I will give specific projects and project examples where heat batteries have been used to achieve outcomes which are conducive to the decarbonization of our heating and cooling sector. Now, if you do have questions throughout the presentation, please put those into the chat if you want, or note them down, and there should be there will be enough time at the end of the presentation, I think, to address those questions. Yeah, so regarding my first point, what is a heat battery or thermal battery? This is essentially the definition of a heat battery. Heat batteries are thermal stores storing energy from various sources and providing it as useful heat or cold energy using phase change materials. Now, if we dig in a little bit into what's behind that sentence, first of all, they are thermal stores, which means that they're not storing the end product. So, for example, hot potable water or system water, but the energy that is required to heat that, to bring that water to temperature. Also, they store energy from a variety of different sources. Our products accept direct electric input. They accept input from heat pumps. They accept input from boilers and other heat or cold sources available. They're also providing this in the form of they're storing this heat and or cold energy, and they provide it as useful heat or cold energy. What that means or leads to, and I will get back to that a little bit later, is that they can use energy that is at a low rate, but provide a much higher rate output than the input. And that's one of the key benefits that thermal stores and heat batteries bring. And last but not least, they're using phase change materials. And that brings me to the question, what are phase change materials? Probably the most well-known phase change material globally is water. Water, as you will all know, changes phase, first of all, when it melts from a solid to a liquid state. And then later on, when it evaporates from its liquid state to its gaseous state. The melting process happens at a temperature of 0 degrees Celsius, whereas the evaporation process happens at a temperature of 100 degrees Celsius, depending on whether you're at sea level or not. Now, the power of that phase change process and the thing that really brings the core benefit to our heat batteries as well is the fact that the change in state requires stores a very high amount of energy, or requires a very high amount of energy. And in fact, if we look at water, the change from a solid block of 1 kilogram of ice at 0 degrees Celsius to 1 kilogram of liquid water at 0 degrees Celsius, so no temperature change, requires the same amount of energy than bringing that kilogram of water from 0 degrees Celsius to 80 degrees Celsius. So this this phase change stores a lot of energy, which is known as latent heat, instead of sensible heat, which obviously brings a change in sensible temperature. And water is by no means the only material that provides these or that has these these characteristics. And one quite well-known material is, for example, the one that you find in these little hand warmer pouches. It's called sodium acetate trihydrate. It's a material that instead of melting and freezing or solidifying and melting at 0 degrees Celsius, changes its state from solid to liquid at 58 degrees centigrade. And that is true in both ways. So the phase change always happens at the phase transition temperature. And at that temperature, phase change materials will absorb significantly more energy without changing their temperature than materials that at this temperature are in a are still in their sensible heat phase. So what that means is that at the temperature of 58 degrees centigrade, the material that we use, which is sodium acetate trihydrate, I said it before, with additives, stabilizing additives, stores about 4 times as much energy than water. And this is specifically around the use case of for hot water provision. Actually, if you look at other use cases, for example, the use case of space heating, where there is a much narrower delta T across the or around the phase transition temperature, you will find that the benefit that we bring in comparison to water storage is even higher. And that brings me really to a core concept and a core benefit that heat batteries have over water-based storage systems, or actually not only water-based storage systems, but any storage systems that, or thermal storage systems that are based on sensible heat rather than latent heat. And that is that within the same space envelope, you can do 2 things. Either you can have the same amount of thermal energy stored in a significantly smaller space. In this case, we are about 3.5 times smaller in terms of the envelope, space envelope, as an unvented cylinder. Or alternatively, you could also pack significantly more energy storage into the same space, and that is an important point, especially regarding flexibility provision to the energy market, which I will speak about later. So when we look at the, sorry, I just put these in at the last minute. So there's some logos on here. I'm sorry about that. When we therefore look at the systems, yeah, we provide the same amount, and this is a picture from our experience room in Scotland, and the tank on the left-hand side has the equivalent amount of hot water and energy store, or provides the equivalent amount of hot water as the heat battery on the right-hand side. And the material that we use, sodium acetate trihydrate, is non-toxic and it's non-flammable, which is very important for safety aspects. In fact, the material is sometimes being used as flavoring in salt and vinegar crisps. Another important aspect of the product itself is that because we don't store hot water, or potable water in this case. First of all, we're not a large pressurized vessel. We have less than 15 liters of water content in any of our product sizes for the residential sector. And secondly, all the water will always be replenished and replaced very, very swiftly, even with very small drafts. And that means that all the risks that usually occur around Legionella, etc., are significantly reduced. And I would even go as far as saying that they are essentially eliminated because of the nature of the sodium acetate trihydrate in there, the phase change material. We have to store heat at temperatures above 60 degrees all the time anyways. Just a couple of other things, because because you can use, we're not as constrained in terms of the form factors that we use to store the energy, because we're A, not a pressurized vessel, and we B, have a much smaller volume. So we do not require the same amount of work to maximize the volume inside our product, and therefore we can use vacuum insulation panels because we are essentially just a box. Which allows us to provide extremely energy efficient products as well. Our equivalent of a 300 liter tank or 280 liter tank has heat losses of only 35 watts, which is about half of the energy losses of the closest unvented cylinder on the UK market at the moment, at least of those widely sold that we're aware of. Just for completeness and fullness, on the right-hand side here, you see the label, the energy label for a product. Electric water heater or a direct water heater. That has a much lower label, a C, which is essentially just a penalty that is built into the regulations for the use of direct electricity. But the level of insulation and the quality of the insulation is exactly the same across these two. When we look at water tanks that are installed in the UK stock today, older water tanks, the benefits will be actually even higher. And based on an analysis that we've carried out in the market, essentially the heat losses will be the efficiency of the product is about 4.5 times higher than these old systems that you will still find quite regularly in the UK. And that leads to a reduction in energy bills, or can lead to a reduction in energy bills of up to £160 just by the replacement of the tank with a heat battery and the reduction of the losses that come with that. Another thing is longevity, and this was really one of the core elements. And maybe I first show this slide. Longevity was the key element that we had to achieve to commercialize PCM heat storage. And it was the thing that was holding back the technology up until now. Phase change materials tend to separate and disintegrate after some time of use, and most of our early work, essentially the whole period between 2006 and 2013, was focused on finding a way to make these systems or make these materials stable, and we have achieved that, and we've actually tested the material in our own labs for more than 40,000 cycles with less than 10% reduction in terms of the energy storage capacity. To give you an idea, 40,000 cycles is equivalent to around 50 years, to more than 50 years actually, of lifetime on 2 cycles every day, so 2 full charges and discharges. And we've also had this verified externally by a third party, RAL quality mark. RAL has a quality mark for phase change materials, and we have achieved their highest grade, which is the grade A, which unfortunately, because they had never seen anything as high, only goes to 10,000 cycles or over 10,000 cycles, and they had no measurable degradation over this number of cycles. The other point about longevity is that our heating elements, which we have in some of our products, are not sitting in water, and therefore essentially they are shielded from the varying quality of water that you can have, and this allows us to give a very long warranty on the product itself, including the heating element. One thing I want to point out is that obviously currently the core product is around the 58-degree material, but this is by no means the only phase change material that we are either researching or already offering into specific project applications. And as you can see here, there's a wide range from very cold materials for the frozen food and process cooling, all the way up to very high temperature materials to provide energy for process heat. None of this really is very new in terms of its concept, but the question then is, why is this coming up now? Why do we think that heat batteries and latent heat thermal storage is essentially at a breakthrough moment in history? The concept really is quite old. The first time it was described and researched was by Joseph Black, which was a professor in medicine and chemistry, both in Glasgow and later in Edinburgh. And he first described this concept in the 18th century while researching at Glasgow University. And the first application of the concept for the use of heating and as a heat battery really was in the 40s, late 40s, early 50s in the US by a researcher called Maria Telkes. She was an inventor, a very prolific inventor and researcher at the Massachusetts Institute of Technology. And she was commissioned to develop a house that was to be heated entirely by solar thermal inputs. And this is known as the Dover Sun House. And the way she achieved that is what you can see here in the picture. So first of all, obviously a very large south-facing aperture, but also she used that aperture to trap infrared from the sun, both in summer and winter, and circulate the heated air into a bank of phase change material that was storing energy at a much lower temperature than we do with our current material. I think she used a material at around 28 or 30 degrees. And this system actually worked really well. It worked really, really well for about 3 years. And after 3 years, she ran into the problem that I've already described, and that really has been holding back latent heat thermal storage since really since its discovery by Joseph Black, which was the fact that the material that she was using was separating, and essentially the thermal storage capacity of the heat battery that she used in the house broke down completely, and the system wasn't operational or functional anymore. And this was really what we focused on with in cooperation with the University of Edinburgh, especially Professor Colin Pullham of the University of Edinburgh and David Oliver, back then a PhD student who was supported by Sunamp, and who really made that breakthrough in terms of stabilizing that material. I've already talked about this, and this is really why we can now confidently say that heat batteries are ready for the market. And just to give you an idea, this financial year we will be shipping our 10,000th heat battery core, and we have now produced around 6,000 products of our latest generation. In terms of how heat batteries can be used, they are really quite versatile, as long as the boundary conditions that the materials that are used inside the batteries are met. The boundary conditions for the materials are always defined by really 3 temperatures. The first temperature is the upper limit, which is the temperature at which the material would take damage and separate or degrade, which obviously can never be exceeded. The second temperature is it's 4 temperatures that define the material. The second temperature is the recharge, the minimum recharge temperature, which will always, depending on the design of the product and also on the material inside, sit around 5 to 7 Kelvin above the phase change temperature. Then we have the phase change temperature, of course, and then we have a temperature at which heat can be extracted from the heat battery, which is usually about 2 to 3 Kelvin below the phase transition temperature, depending again on flow rates, etc. In terms of the services that can be provided, as you will have seen from the slide before about the temperature or different temperatures of materials that we have, this ranges all the way from cooling, both cooling in the sense of process and product cooling, to air conditioning on one hand, and to process heat and or hot water on the other hand. And as inputs, I already mentioned that we can accept direct electricity, but we also can accept district heating or cooling. We can accept heat from heat pumps, chillers or air conditioners. And we have the means to use PV and potentially also solar thermal, or also existing boilers or biomass systems. Now, why are heat batteries important? I've already shown this slide before. Obviously, today is the day where the US will sign up again for the Paris Agreement, which then essentially brings us to 190 states having signed up to the agreement, which really is essentially almost all UN parties. And what that means is that it sets us very firmly on a trajectory of reaching net zero emissions globally. And for the UK, the target is to reach those by 2050. That means we not only have to decarbonize our heating and cooling, we also have to decarbonize our electricity sector and our transport sector, of course. And if we look at electricity, a lot of work has already been done in that area. This is a screenshot from April last year, but there's actually more impressive values out there even today, which shows that for large parts of the UK, we are already benefiting from almost carbon-free electricity, especially up here in Scotland, where Sunamp is based. And even on days which are have now to be considered as high carbon intensity days, this was only last week. We have overall the highest factor that we see here is a factor of 350 grams per kilowatt hour in the south of England, which is essentially lower than the average carbon emissions for electricity even just 6-7 years ago. Factors which, by the way, we're still using today to design our houses, which essentially has quite adverse effects on building design today. The fact that electricity has already been decarbonized largely has been taken into account, amongst others, by the Committee on Climate Change, which essentially in their analysis foresees a very high requirement for the uptake of heat pumps, and therefore for an electrification of heating in the UK. Which brings us to one of the 4 questions I want to look at, which is how we will heat our homes in the future. The second question is the question how we are heating our homes today, and the challenges that essentially combining how we heat our homes today with how we should be heating them in the future, what challenges that brings, and how thermal storage can help overcome these challenges. The third question I will address here is how we can ensure that consumers don't face higher energy bills, and what role flexibility will play in that in that endeavor. And then the fourth, and by no means last but not least question, is how all of this affects our energy system going forward, and how the energy system as a whole will be able to cope with these, and how thermal storage can essentially provide a lot of relief in that area. So I've already mentioned that one of the applications of heat batteries is that you can store the same amount of energy and provide the same amount, therefore, of useful services like showers and baths to people in a significantly smaller space. And why is that important? The reason why that is important is because in the UK in particular, not everybody has the amount of space to put a 300-litre hot water tank in. And heat batteries are really, in this case, an enabling technology because they enable thermal storage for hot water provision by heat pumps, for example, in even the smallest of spaces. And one example for this is a project down in Sunderland. If you Google after this for Core 364, Core 364, you will find quite a lot of information about this project, and also a little YouTube video for which I've put a link here. And in this project, Gen 2, which is a housing association, was facing the fact that they had 7 towers with a total of 364 apartments, all of which had combi boilers installed. Now, they had 2 major issues, 3 issues really. 2 of them really crucial for them. First of all, the fire risk. On the backdrop of the Grenfell disaster, really one of their key concerns was trying to get anything flammable or anything that would increase flammability out of these apartments. The second concern was the fact that pure and simply those systems were coming up to the end of their lives anyways. They were having more and more breakdowns, and essentially they wanted to look at a full replacement of all the systems in the buildings at the same time. And then obviously also a challenge around carbon emissions of these systems. Now, they did look in detail at what the different options for them could be. And essentially what they settled on was to install shared ground loops provided by shared ground loops to run ground source heat pumps, individual ground source heat pumps, one per flat, and to heat the buildings in that way. Now, the challenge that they had was that they were not able to obviously remove the tenants from the building. So all of this had to be installed while the old infrastructure, meaning the gas boilers, were still in place. So while in some apartments the heat pumps and heat batteries were already being installed, in other apartments still had to be heated by their boilers. And that meant that essentially the only place in the apartments that would have been able to fit a normal cylinder, which is this cupboard, wasn't usable at all, and even then it would have been probably too tight, because this is also where the riser for the shared ground loop is, and where all the electronics are situated in the flats. So the only other space where they were able to put a hot water tank in was back here, which is the old boiler cupboard. And essentially, heat batteries in this case were a bit the savior of that particular project, because the only way to get sufficient amounts of hot water storage into this area was by using the heat battery. Because in total this cupboard is just over 40 centimeters wide, and it still had to hold all the plumbing, etc. as well. So what they achieved, therefore, with this project is, first of all, they brought heat pumps into places where previously most people, I think, would agree, would have said that this is absolutely impossible. They've also reduced CO2 emissions by more than 70%. And this is reducing every day that we build more wind turbines and more PV in the UK. They've hugely reduced the fire risk inside the building. They've virtually eliminated the Legionella risk. They have virtually eliminated or reduced significantly the maintenance of the system. A very important aspect from facilities management aspect point of view is that there's no billing issues with the system, because every apartment has their own heat pump, which is on their own electricity meter, and they did not have to decant, which means they did not have to remove the tenants from those buildings while this project was ongoing, because at every given point in time, apart from for individual apartments for a couple of hours, there was either the heat pump or the boiler that was providing hot water and space heating. These are just some other images of installations out there in the field, which essentially show the benefits of using heat batteries and their reduced space profile. Here on the left, you can see the comparison between one of our largest units, the Unit 12, with the space that was previously covered by a hot water tank that was removed from this installation. And as I said before, really what this would allow you to do as well, alternatively, would be to fit significantly more storage into the same space, which is a very important aspect I will come to. The second huge topic around the electrification of heat and therefore the decarbonization of heat is the fact that in the UK we are used to heating our homes on a very let's say, spiky pattern. Essentially, most people will usually have their heating on a timer, which often heats the house up in the morning for a couple of hours. Then when they're at work, it will not be heated, and then it will heat again in the evening. I assume that quite a lot of you, like me, will have their heating on for a lot more these days, because it otherwise gets quite cold in my personal office here. And this is a challenge for two reasons. First of all, because heat pumps will not be able usually to deliver that type of profile because of their response rates, and secondly also because of the strain on the network. But if you use thermal storage, that essentially allows you to completely disassociate the heat demand from the supply of that heat to the storage. What that means is that you can use significantly smaller heat generators, first of all, heat generators that are able to provide the average demand, and also you can use you can provide heating schedules that previously would not have been possible without having any impact in that case on the comfort or the performance of the customers. This is a very important point, which I will also come to for the last bit, because it really allows you to start being quite flexible with when you charge these storage systems, because you're not slavishly following the demand that is being set by the consumer and their patterns, which are quite often very unpredictable and personal. The third point, the question, how can we make sure that we're not leaving customers with extremely high energy bills, is another very important one. And a key aspect of this is the fact that in the future, it will become a lot more important when we will use energy than it will be how much energy we actually use. Today, our whole billing system, our whole, the way we purchase and consume energy, be it gas or electricity in the homes, is essentially built around quantity and not around timing. And this is going to change, in our view, going forward, and it will allow to use energy much more efficiently and cost efficiently. And to give you one example of what can be done, this is a project that we've done up in the Highlands near Oban. And in this case, we went the other way. We did not go for, or actually the client in this case, did not want to go for the least space. They wanted to go for the most amount of storage. And the reason behind and the thinking behind that was that they wanted to enable their tenants to operate their heating systems on an E10 tariff, which is it's not a fully flexible tariff. It's a tariff that provides 10 hours of low-cost electricity spread out over 3 periods throughout the day. And in this case, we installed high-temperature heat pumps in combination with heat batteries to essentially enable exactly that and enable the use of lower-cost electricity. The results of this project, or preliminary results of that project, have shown that first of all, we can fit around 750 to 1,100 liters of water storage, of equivalent water storage, into a standard airing cupboard. But we have also achieved a 59% reduction in carbon emissions and continuously falling, but also a 55% reduction in running costs and have achieved the energy efficiency rating targets for these buildings that the housing association was aiming for. And this story of being able to achieve lower running costs with heat pumps is a story that we have not only shown in this project, we've also shown this in previous projects. And the important thing here is we've also shown and demonstrated this on gas. In 2013, we won a grant back in the day from DECC, an SBRI, Small Business Research Initiative grant, that really was the kickstart of production of heat batteries for us, and allowed us to install the first heat batteries in actual homes. And in that project, we had quite a few installations where we were replacing old night storage heaters. And in those cases, it's quite obvious if you replace night storage heaters with heat pumps, you will always achieve quite significant energy and bill savings. But the one that I would like to point out here on the right-hand side is this house here. This is the house of our CEO, and it was essentially almost a requirement of essentially, if you think that this is suitable and can be used, then you should also install it yourself. And he had in his house beforehand a gas boiler installed. And this was replaced by heat batteries and a high temperature heat pump on an E10 tariff again. And the important thing here is that in this building, we achieved a 77% reduction in energy use. We also, and this is the really interesting point, achieved a 50% reduction in the energy bill because of that. And obviously a huge reduction in carbon emissions, 46% back then, which by now we think is, given the current carbon profile in Scotland, will be much closer to 90% over the year than 46. All of these things are not only true for the residential sector, they also apply to commercial and industrial applications. And one example I want to highlight is a project that we've carried out in France in 2020, where we've used one of our products that stores cold energy at 5 degrees Celsius, essentially to enable the extension of a heat network in a large city center. So there were a number of buildings that wanted to connect to that heat network. The problem was that at this point in the network, they would have been able to fulfill the energy demand over a 24-hour period easily, but they were not in a position where they would have been able to fulfill the energy demand in the peak period. So what they needed to achieve was essentially thermal buffering to allow the extension of that network. And because it is a city center, a very high density urban center, they were extremely constrained in terms of their space, and they chose our largest product, which is currently available, to provide 400 kilowatt hours of storage at this temperature level, to provide enough buffering to shave the peak demand and spread it out over a 24-hour period, so that they were able to recharge the buffers during those times where the cooling wasn't required. And that really brings me to the last point, which is what will be the impact of thermal storage and heat batteries on our overall energy system. I want to use a graph here, which probably a lot of you will have seen before, and it has been used and also misused a lot in the past, usually with the message of, oh, look at all these, oh, look at these spikes, look at all this energy demand, up to 7 times higher than we currently have in our electricity system. It's absolutely impossible that we ever electrify heating in the UK. The thing with this graph is that this shows a half-hourly demand profile condensed over 10 centimeters, a full year's worth of half-hourly data points, so around 16, well, almost 18,000 data points. And obviously, this gives the impression that these are really, really solid blocks of energy demand here, and that there's a huge problem, because not only is the peak significantly higher, but also the overall demand is significantly higher. But if you zoom into this data, and we were kindly provided with this data by Robert Sansom, who created this original graph, what the red what the gas demand here in red actually looks like is the chart that I've shown you earlier. And what I've shown you earlier before as well is that if you spread the same amount of energy demand over a 24-hour period, you significantly reduce the level of demand, and therefore the impact on the networks. If you do the same exercise for the data in this graph, what you will find is that over a 24-hour period, the overall demand is significantly lower than the peaks that are shown in the red. So this is the green line in this graph, which is essentially just taking the total demand over the 24-hour period and spreading it over the 24 hours on a level basis. And if we then take into account that this heat could be supplied by heat pumps with their advantage in terms of efficiency and COP, all of a sudden you'll find that there is still a huge challenge. I mean, don't get me wrong here, there is still a huge challenge, but the peak demand is all of a sudden within the boundaries of the capacity that we are already seeing on the networks today. So we're not speaking anymore about an increase of 7-fold or 8-fold in terms of peak electricity demand. We're speaking now about an increase, roughly a doubling of peak demand in the electricity network, and this with the onset of flexibility from EVs, etc., the flexibility will increase even further. And yeah, that really brings me to the conclusion, which is that first of all, that heat batteries are here today. They're revolutionizing how we store heat and cold energy, because mostly because they are an enabling technology for the decarbonization of heat, because they solve our space problems. They deliver what the consumers have come to expect from their heating. They bring the benefits of flexibility to homes and industry, and they stabilize the network by enabling a large-scale demand response. And that really is why we think that heat batteries will revolutionize the way we store thermal energy in the future. And that's everything from my side. I think I've overrun a little bit, but yeah, if there are any questions.
Thanks very much, Lucas, for the excellent presentation. Guys, you can unmute your microphone and ask questions or put your questions in the chat.
So we have one question here, whether the occupants found any differences or changes in heat supply, and whether they were satisfied with the new systems, and whether there were any issues. Generally, what we found is that in the projects where we installed the storage, was that the experience of heating actually improved. There's a wide range of different case studies that we have on this. To name one, there was one example. I mean, this was, to be honest, an example of very bad system design as well, where a household was they had an E10 tariff, so a high and low cost period tariff, but this was used to run a flow boiler. So no storage in those houses at all. And what that led to was that there was a huge zigzag profile of overheating and getting too cold in those buildings. And there, the introduction of the storage actually allowed us to completely level out the temperature profile. So instead of being always too hot and then too cold, people were comfortable throughout. It's really the same experience that we find with other applications. When you use heat batteries in combination with heat pumps, for example, one thing that the heat batteries allow you to do, and I alluded to this a little bit earlier, is to serve as a multiplier of capacity for shorter periods of time. So we can heat radiators faster even than a gas boiler, because we have an instantaneous power output of upwards of 40 kilowatts. Obviously, would only sustain that for a couple of minutes if you were doing that the whole time, but we can put an enormous amount of energy into the heating circuit at startup if we want to or need to, and that's really important from a customer experience point of view, because people are used to having their radiators warm up quickly, and also to their internal temperatures reacting quite quickly when they, for example, increase the set point on their system, and they're not used to waiting for an hour or 40 minutes or something like that for a heat pump that starts running to gradually lift the flow temperature and therefore the room temperature, and that is really where thermal storage in general, to be honest, but heat batteries in particular, allow you to I think improve the customer experience of their new heating systems dramatically. We've got one question here, which is, at what temperature does the high temperature heat pump need to deliver heating water to the battery? How long does it take? Okay, so the temperature at which the heat needs to be delivered by the high temperature heat pump to the battery for the 58 material is about 65 degrees. This is essentially just to ensure that there's enough heat transfer into the material. There is obviously always then the comeback on that, which is, oh, this is really high, this is really bad for the efficiency, etc. However, there are 2 points from our side on that. First of all, in terms of hot water provision, the significantly reduced thermal losses of our heat batteries actually almost cancel out the losses in efficiency, and the fact that we don't require a a Legionella sanitization cycle means that we are essentially roughly on par with a hot water tank that is heated to a lower temperature and goes through a weekly sanitation Legionella cycle. On space heating, there are obviously impacts on the overall system efficiency from that requirement. However, these are hugely outweighed by the ability to use lower cost electricity by charging the batteries at the times when the electricity is cheapest. And these times are usually not the times when heating is required. And in our projects, we've demonstrated that essentially the financial COP of the product and combination is much better, even though the physical COP in terms of energy is lower. Another point to mention here is that we do have other temperature materials, one at 48 degrees and one at 43 degrees, which are obviously much more geared towards lower temperature and therefore higher efficiency. But they require then obviously a lower temperature heat distribution network, etc. One of the key points here really is that the system allows minimal changes inside the buildings and still use heat pumps efficiently. Okay, so I've got quite a few other questions. There's a question on the effect of continuously charging and discharging on the battery lifespan. As I said earlier, we have tested our material over over 40,000 cycles in our lab. On a 2 cycles per day, that is equivalent to more than 50 years of lifetime. And at the end of that test, we had still less than 10% in reduction in storage capacity. And effectively, this would also be could be regenerated by re-adding some of the lost some of the components of the material that are lost over that time period. And we've also had that validated, obviously, by RAL PCM. Yeah, then there is the question here that at the end of the life cycle, the PCM can be recycled. The question here is whether that's a practical and established process or just in theory. To be quite honest, at the moment, this is a theory because none of our heat batteries have been in the field for 20 years or 30 or 40. So we haven't really had to recycle any of that material. But essentially, the material itself does not undergo significant degradation. And we know we understand the chemical processes that do occur very well, and we also know how to counter them, and therefore how to essentially make the product usable again. The other thing is that in principle, this material can also be reused in other applications. This particular material is sometimes used as de-icer on runways and other applications. But again, at the moment, we're not at all at a stage where we essentially had to look into building up that reuse supply chain simply because the products aren't in the field long enough. Yeah, there's a question here about prices. A couple of questions about prices. So one here, heat batteries seem expensive today, and how soon do I think that the price may become competitive with buffer tanks and other alternatives? So that's an interesting question, because actually our heat batteries are today competitive with the upper third of the cylinder market in the UK. We are competitive today with the top unvented cylinder brands in the UK. Not entirely on capex yet. That has to be said, but we're working on that really hard. But even with a slightly higher capex today, if you look at the life cycle costs of our product, we are competitive today, and actually we repay within a very reasonable period of around 5 years. And this is, as I said, before any future cost reductions. I mean, hot water tanks have been around for a very long time, and there's very, very, very little margin there for future reductions in prices and costs. Whereas really we are still very much at the start of our experience and learning curve and cost curve. So I would expect to see the prices of heat batteries come down in the future. But also one thing to point out is that even today, we are now at a stage where we are regularly specified into projects, and we're also sold into end customer applications. So while we are still a higher priced product, but obviously also with a huge amount of additional benefits, we are competitive today. There's another question on payback on replacing a gas boiler and radiator system with high temperature heat pump and thermal battery. This is always the question that is the hardest to answer, because it really depends on the on all the essentially things that surround that install. It depends on the size of the heat pump. It depends on the gas boiler that is being taken out. So yeah, I can't give you an easy answer on that question right now, because I haven't got a case study here. Then yeah, one question actually from an earlier question regarding the temperature that the heat pump needs to provide to the heat battery was how long it takes to heat a battery by just using the heat pump. Again, this will depend very much on the system combination that is in place. Our heat batteries for residential purposes currently range from 3.5 kilowatt hours for the smallest for hot water applications, to 14 kilowatt hours of thermal storage for the largest, and then depending on the size and capacity of the heat pump, essentially that will give you the typical recharge time of the system. Flow temperatures we've looked at. Yeah, there's one question here whether the heat batteries do need a constant flow temperature to store heat. Yes, they do. Essentially, in order to you always need to be above the phase transition temperature. You need to maintain a delta T of ideally around 7 degrees between the phase transition temperature and the inlet temperature on the primary circuit, in order to essentially guarantee a rapid enough recharge time. There's one question here regarding government subsidies for average customers. Yes, there are. So under the Green Homes Grant, and now I need to make sure that I get this exactly right, only heat pumps, solar thermal, and other heating measures and other measures are eligible as primary measures, and then there's a number of secondary measures. However, when you do install a heat pump, thermal storage for hot water provision, and that includes heat batteries, are eligible as auxiliary items and components to that installation. So essentially we are covered by the Green Homes Grant, but at the moment only in combination with a heat pump, which is essentially just how the system is, the grant is built today. The heat battery is one of the applications that is seeing quite a lot of success today in the market as well, is by using it to store energy from PV, and to use that energy either just to provide hot water directly, or another option is to use the heat stored in the heat battery to provide preheating to a gas combi boiler. There are some combi boilers on the market which can accept preheated water on the hot water side, and you can then essentially use the electricity from your PV to substitute the gas for your hot water demand. And I think that's all the questions. Are there any other questions?
I think you answered a lot. Okay, can I ask everybody to unmute your microphone and clap, and thanks Lucas for his great presentation. Thank you, Lucas. Thank you.
Thanks a lot. Yeah, and if there are any further questions, if you want to have more information, you've got my contact details here on the screen, and I think I assume that the presentation will also be shared after this meeting. So always drop me a message and email. Okay.
Okay, thanks very much, Lucas. Thank you. Thank you, everybody.
Thanks a lot, everybody, and have a really nice evening.
Thank you. Bye.
Thanks.
Bye.
Bye.